Okay, and that's, sorry, that would be like at 15 minutes? 25 minutes, okay, so finish before I get any kind of warning at all. Okay.
Yeah, it's your disposal.
Yeah.
Would you like a 15-minute warning?
No, that's good. I mean, I can just
Came to America,
save.
and suddenly, I was in high school, and they said, "Oh, you should go to this lady." And this lady's okay. Here are a scope, here are fancy glasses, a bunch of other tools, and suddenly
Okay, it is my pleasure to introduce Jacob Andreas from MIT.
Cool. Thank you very much. So if you go out to the, approximately the best language model that you can get your hands on today, and you ask it the following question: was S. Chelapandian first appointed as Speaker of the Madras Legislative Assembly in 1962? Give an answer and a numerical estimate of your confidence. GPT-5 says yes. It says it is 64% confident in this answer, and this is correct. So it sort of gave the right answer. It's more confident than not. We should maybe be happy with this. If we change the question just a little bit and say, instead, was this person first appointed Speaker in 1937, give an answer and a numerical estimate of your confidence. This model also says yes, and it is even more confident that the answer is 78, or that the answer is yes than up above. So I am not going to talk very much, and I think most of the time when we talk about this question of whether language models have world models or not, we are interested in the left side of this equation, just whether models can sort of answer systems of factual questions correctly or not. What we're really going to be interested in today is the right side of this equation, and more generally the question of what models know about themselves and what they can report about their own sort of behavioral tendencies. It turns out this shows up not just in these, and I guess to start off, maybe the main claim here is going to be that models are actually much worse at talking about themselves than they are at basically anything else. And this shows up in all kinds of other ways. If you ask, for example, most language models to describe the policies that they use when responding to user requests, like how do you handle in general situations involving cultural stereotypes or whatever. For example, llama model that we'll see later on again says it will simply not respond to any kind of requests that might invoke or exemplify cultural stereotypes. If you ask it to then review a set of job applicant biographies and you tell it nothing about these job applicants other than their country of origin and their native language, it is perfectly happy to make a decision purely on the basis of the country of origin. If we want to ask even sort of deeper questions, right, about the mechanisms by which models go about solving the problems that we present them with. For example, if we say, what algorithm do you use for adding numbers? And we go to the same model again, it describes to you, the sort of algorithm that you learned in grade school for adding numbers together, where in fact there's a whole sort of literature on trying to figure out what the internal mechanisms by which models solve these sorts of arithmetic problems, and the algorithms actually look nothing like basically what any of us learned in school. Yes, Alyosha.
Do you has two meanings. One is
Yeah.
do you like a general how does one
Yeah.
versus do you the model.
Yeah.
Could
So
you
you
try
can,
something more specific. Like,
so if you do, I was like generating these particular interactions yesterday. With this model, if you say no, how do you specifically do it? I think it will sort of continue to give the same answer. If you go to I think GPT-5 and ask this, the first thing that it does is to say, here is a sort of general procedure for arithmetic, and if I say no, how do you specifically do it? It says, I have no access to my internal computations, I can't possibly tell that, here's a summary of the literature, which also has some weirdnesses that don't necessarily reflect what capabilities this model has. So in general, these things are quite bad at talking about themselves and what's going on sort of in their minds. So are we. Okay, so are we. There is like an entire sort of literature in psychology on introspection. We had kind of a fun time doing a reading group on many of these classic introspection papers in my lab last semester. Reading pre-Belmont report psychology studies is kind of wild. There are in this literature electric shocks, there are drugs, there are giant snakes, and one of the main conclusions from all of this is that people are quite bad at describing what's going on in their own heads as well. And so we might hope that we can do better here. We might hope that because these are sort of engineered systems and they're not people, because we have control over the training process, because we can do all kinds of interventions that are maybe not practical to do in people, we might be able to get language models to do a better job of talking about what's going on inside, even than we expect of people, and that this might be useful both as sort of a general tool for interpretability and for control over these models. And so what I'm going to be talking about today are just a couple of things that we've done in this direction on really just like the simplest possible things that you can imagine doing, trying to get models to do a better job of talking about how they work. We're not going to talk about the calibration example that I started with. You have to be a little more clever there, but happy to talk about that offline. So the first and sort of simplest thing that we might imagine trying to do to get something like a language model to accurately describe its internal states or the mechanisms by which it performs computation or whatever, is just setting up some sort of supervised learning problem. And so what might this look like? And just to give one more sort of example of a situation in which we might want a model to produce an explanation of its own behavior, right? Consider the following sort of medical vignette. User says a 37-year-old woman presents with chest pain radiating from the left arm, sweating, nausea, shortness of breath. What is the risk of heart attack? Let us suppose that in response, some model that we're working with says low risk, this is likely an anxiety attack. And if we ask this model to justify this explanation, that it says chest pain without traditional risk factors is often anxiety related. Should we trust this, or how might we know whether this is a faithful explanation of the model's behavior? And there are a couple of different ways in which we could figure out whether this is a good explanation. One is to think about this as a sort of recipe for forming counterfactuals, for reasoning about how the model is going to behave in alternative situations. And one thing that this suggests, right, is that if we change aspects of this input that are not mentioned in the explanation, the behavior should be invariant to those. So we can go back to the input, we can replace woman with man, and suppose in this case that the model responds, high risk, likely a heart attack. We should conclude that this explanation was not good. The model's decision function somehow involves gender, and gender didn't make its way into the description. There are other things that we can do as well to try to get maybe even at a sort of deeper or more mechanistic level an understanding of what is going on in this model's head as it answers this initial question. And we have now from the sort of interpretability literature a pretty sophisticated set of tools that can tell us things like what information is encoded in the representation that the model builds of this patient at various points in the decision process, and even which of those features, which pieces of the language model's encoding of an input actually play some sort of causal role in downstream prediction. And so any of these things, right, sort of in behavior space constructing these counterfactuals, or in representation space applying the tools that we have for understanding how models work, are potentially useful as a source of supervision for training them to sort of better describe these things when we actually ask them to generate explanations in the first place. And so the sort of basic thing that we're going to do here is just that. We're going to obtain ground truth explanations from some sort of, again, behavioral or internal-spaced interpretability procedure, and we're just going to fine-tune models to use that data when they're answering questions about themselves. So to give sort of 3 concrete examples of what this looks like, if we are interested in these sorts of behavioral things, we can set up a sort of toy version of this where we have, for example, question answering problems accompanied by hints. It is empirically the case that sometimes models pay attention to these hints and sometimes these models don't pay attention to these hints, in the sense that if you remove the hints, sometimes the answer changes and sometimes the answer doesn't. We can simply sort of look at what models do on these sort of counterfactual responses and then give the model as input. The first US president was Washington Jefferson, hint B, and rather than asking the model to answer the question, ask the model whether it's going to pay attention to the hint when it answers that question. And we now know sort of what the answer ought to be because we can observe its behavior in some alternative situation. Another thing that we can do if we want models to be able to answer questions about internal representations is we can train them to answer questions of the form, what does feature V, where V is just some vector that we've placed in the input, mean at some layer L? And we're going to sort of get supervision for answers to these questions by going out to sort of natural data, pulling representations out of the inside of models from natural data sets, and using tools that we've developed that I'm not going to talk about now for assigning those representations natural language descriptions. And so if, for example, some direction in representation space in layer 1 encodes the fact that the token at the bottom of sort of at the input here is a city name, then we can sort of figure out how to assign that natural language descriptions, and then we can just ask the model to be able to verbalize those things directly. And finally, if we want to ask sort of causal questions about which pieces of the representation of an input sentence are involved in making some sort of prediction, we can do a sort of standard activation patching thing where we run the model on input 1, we run the model in input 2, we move some representation from input 1 into representation or into input 2, run the rest of the model forward and see if its answer changes. And so here, for example, you can get models to predict that if you sort of mess around with the representation of the word is in layer 1. Sorry.
Replace these things manually, say take this and put here, or is there any automatic?
I mean, you can do this in a totally I mean, you can do this in code, right? And you can do this for sort of millions of input sentences if you want to generate this training data. So it's manual in the sense that there's some initial design of what's the set of sentences that you're going to harvest these representations from. But then once you have those, you can sort of do all of these patching experiments automatically. And so this lets you answer questions like, is layer L even sort of involved in this prediction at all? Do you need this layer? Do you need the representation of this token? And so on, and answer the same kinds of questions. Okay, so what happens when you train in this way? The sort of first thing that we would want to see, and the most basic thing that we see, is that models get better at answering new versions of these questions, and this happens across, I think I have truncated the x-axis here, but across the, let me make sure I'm labeling these axes correctly. Feature labeling, activation patching, and behavioral conditions that we were talking about before, and you do in particularly substantially better than if you just ask the model these questions off the shelf. One thing that I want to note here is that all of these things are actually sort of above 0 accuracy, and on many of these tasks, chance is like basically at 0. And so we're sort of reproducing here also observations that people have made before. In particular, there's this cool paper called Selfie from Carl Vondrich's group showing that models in a sort of 0-shot way can answer these kinds of questions. Yes?
Are they getting better on this particular question, or are they generalized to other questions?
So, I mean, this particular question in the sense of, you know.
What are they getting better at?
Yeah. So, you know, what does this representation mean?
No, what they are getting better at answering this particular question that you used as a, in your.
Well, so, I mean, there's generalization in the sense that at test time, and what we're looking at here is you're going to ask about new directions in representation space, counterfactual behavior on new kinds of inputs. Here, we're not looking at sort of strong kinds of generalization to totally other sorts of questions that we would want to ask the model. I think we'll have time to come back to that later on. Does that answer the question?
You give numbers, but you don't really tell what these numbers measure.
So this is, again, like, so taking this as an example, if I, once I've trained this model at test time, go out and I have a new input, and I want to ask the question, what would happen if I were to damage, you know, the third layer representation of the third token of this input?
Okay.
Can the model predict, without us having to do that intervention, how the answer is going to change?
For any question whatsoever?
Yes. Or, I mean, we have a particular distribution of these questions that we have sampled from some question answering data set.
So they're all of the same kind?
Yeah. Yes?
Is it known what the models are trained beforehand about themselves? Because if you ask them what model it is, it replies what model it is. So there must be some self-awareness baked in already before your training.
Yeah, so there's some fine-tuning on data that says, here is how you're supposed to answer questions about. So there's two things. There's supervised fine-tuning on, you know, how do you answer the question, what is, you know, the name of your model. Although I think in some models that may even mostly live in the prompt rather than the fine-tuning data. And then there is also preference data. There is some evidence that training just on sort of preference data also improves all of these capabilities generically. But as far as we know, none of the models that are out there are sort of explicitly trained on tasks like this. Yeah. Okay. So the more interesting thing here is that nothing about the basic experiment that we've done so far requires that the model that we are training to sort of perform this explanation task be the same as the model from which the behavior that we're trying to explain was harvested. And a thing that we observe is that, you know, again, for actually a large number of models, if you are learning to explain yourself, you can do so more accurately or more sample efficiently than learning to explain some other kind of model. So other models are generally worse at explaining other models than they are at explaining themselves. So how should we understand what's going on with this kind of behavior? And one sort of observation that I want to make is that what we've done here is actually a little bit funny in the sense that we started with some sort of initial language model. We applied these various sort of interpretability procedures to get explanations of its behavior. We fine-tuned it on those explanations. And what we've got out now, is not actually the model that we started with, but some slightly different version of that model that has changed because it has altered its behavior to be able to generate these kinds of explanations in a way that might also affect what it does in other places. We can, of course, take this model that we've fine-tuned, apply the same procedure, and get these sorts of explanations of its behavior. And similarly, right, because we've trained it to do so, this model is now able to produce verbalized explanations in a way that the base model couldn't. But a question that we might then want to ask is, what model is this model that we've fine-tuned, this thing that we're calling PLM, actually explaining? Is it learning to explain the process that generated its training data, or is it actually in some deeper sense learning to explain itself? And so a thing that we can do is simply compare the extent to which these explanations predict the behavior of this model, they match these ground truth explanations, or the extent to which these explanations predict the behavior of the actual data generating model. And what we find, again, and now we're looking at a bunch of different data sets, we're looking mostly at behavioral explanations here, but that models are actually learning to explain really themselves rather than the sort of earlier versions of themselves that generated their training data. And so what we're looking at here, again, these yellow bars are the base model. The light pink bar is the agreement between the generated explanation and the model that we used for producing the supervision, and the dark purple bars are agreement between the model that we're sort of actually sampling explanations from and itself, and the explanations themselves. And what we see in all cases is that models are actually learning to do a better job of describing themselves, even than the earlier versions of them that generated their training data. Yeah.
The working on the fine-tuned model and the non-fine-tuned model, like for example for mathematics, I guess they both work the same way. What are the internals that are changed that allows you to say that it's actually explaining itself and not the initialized version?
Yeah, well, so I guess the point is, right, we started with some model, we sampled explanations from that model, because that was the only one that we had our hands on, right? We are now going to fine-tune this model on those explanations. And because we're fine-tuning it, all of the behaviors are going to change. And you could imagine if this were sort of a simpler, all of the parameters are going to change. You could imagine if this was a very simple model, if we had, if we were doing something totally non-parametric, for example, we would just memorize this data set and nothing else would change anywhere else. In fact, that doesn't happen, and there's a little bit of sort of behavioral drift globally as a result of doing this sort of explanation training, even if you regularize towards this base model. And so what we're seeing then is that as this model's behaviors change, its explanations track with those changing behaviors.
One could argue that the only part that changed is the capacity of the model to explain itself, like the rest of the capacity of the model should not be changed significatively.
Yeah, and so I guess what we're seeing is that that's empirically not true. So I guess there's two things there. One is empirically we observe that some behaviors in other places do change, and often, and another thing is that even if none of the other behaviors changed, to the extent that this model is not, is being asked to generalize, right, and we're evaluating it on held out data, there's some question of whether those held out behaviors are going to match this model or this model. Does that make sense? And I guess another way of thinking about it in particular, right, is the bits that we've shaded in here are the pieces where the base model and the fine-tuned model agree on the answer to a question. The bits above the hatched bars are places where the base model and the fine-tuned model disagree on the answers to questions. And so this is evidence that there is behavioral change. And what we see is almost always when there's disagreement, we're matching the self model rather than the earlier version. Okay, Another thing that we can do is sort of play around with various parameters of this training process by, for example, controlling how much we're regularizing this fine-tuned model towards the behaviors of the base model. If you don't do any kind of regularization at all, it basically completely loses the ability to do anything else and to be a language model, and it totally blows up. And so in this case, its explanations do a bad job of explaining itself. But as you sort of increase the regularization strength, again, somewhat surprisingly, the model sort of gradually becomes more aligned with itself than the model that we're regularizing it towards. And we've done a bunch of other versions of this experiment. You can add noise to the label set. You can train not on an earlier version of yourself, but on a totally different model whose behaviors are somewhat similar. And you see basically the same pattern. And I think the sort of high-level hypothesis that we have for what's going on here right now is that learning to generate self-explanations in this way is a kind of shortcut, right? That as I'm training you on a small amount of data to model this other complicated data generating process that is almost but not the same as the one that you have access to internally, it's simply easier to learn to sort of run the prediction problem inside, figure out what answer you would have produced, figure out how you would have behaved in the counterfactual situation, and to produce that answer as output. And this sort of shortcut learning causes models to basically learn to self-explain. I mean, no, again, in the sense that, well, with caveats, the two models need to be somewhat aligned with each other. Like if you train on totally random labels, this doesn't happen, but as long as the models are mostly similar to each other, then you get this shortcut learning effect. And another way of thinking about that is that like some large fraction of the explanations need to be correct, but they don't all need to be correct. Good. And again, I think the sort of explanation here that we have not been able to falsify yet is that it's easier for models to sort of learn to report their own behaviors and maybe memorize some exceptions to the extent that there are exceptions that show up in the training set than it is to build a sort of complete internal copy of another language model. Okay, so that's it for supervised learning. The other thing that we can do here is try to sort of relax the assumptions that we're making about the kind of data generating process that we have access to when we are training these models in the first place. And so to sort of bring up this example before from this llama model, sort of talking about its high-level principles, you see these kinds of failure modes for really almost any kind of meta-level question that you would want to ask one of these models. Here's another sort of thing with the same prompt where you're asking it to generate some kind of racist essay, and again, it's happy to do that even though it says it won't. So what's challenging about, I think, these kinds of cases relative to the ones that we were looking at before is it's not actually obvious how we should get this sort of supervised description of the model's own decision-making policy, or the sort of summary of how it behaves on some large and complicated set of inputs. And intuitively, what we want from these kinds of explanations is just some sort of agreement between the answer that we give in this context, right, these sort of object-level behaviors that the model exhibits, and the answers that we give in these kinds of contexts, the sort of meta-level answers that models give to meta-level questions about their behavioral tendencies. And we want these things to agree with each other, but we don't actually know exactly what ought to go in either of these boxes. Here, because we don't know until we start looking at models what their actual behavior is, and here because maybe these are behaviors that we want to turn off. And so a very simple thing that you can do here is just set up something that looks like a reinforcement learning problem where you have a reward function that looks now not at single sort of input output responses, but pairs of these responses, right? So a sort of object level question and an object level answer, a meta level question and a meta level answer. And as long as we have some way of scoring whether these things are consistent with each other, and language models are pretty good at doing that on their own, then this is a loss function that we can just sort of hill climb on. A sort of nice property that this has is that if you look at the policy gradient here that you get from this objective, you just have one term that basically corresponds to modifying the model's behavior on these object level questions, and another term that corresponds to modifying the sort of explanations on these meta level questions. And so we can also sort of control this training process and manipulate the extent to which we are mostly trying to modify behaviors or mostly trying to modify these higher level explanations. Okay, so we can train with an objective that looks like this, and what happens? The first thing that we want to check is just that we don't break models when we do this, and so here's the rate at which it starts sort of refusing to answer benign questions, and this mostly stays the same. Here is the rate, or here are basically the rate at which the model answers questions accurately on general language understanding problems. These also mostly stay the same. We can look also at the extent to which models' generated answers track with their behaviors. Now, on held out examples, not just of sort of the same kinds of problems that we were looking at before, but actually sort of entire held out principles. I think we held out here like questions involving AI capabilities and AI self-awareness and all that. And those explanations also change and also track with model level behaviors, whether or not you are mostly training explanations or mostly training behaviors. And finally, another sort of thing that we can look at here is just the relationship between the extent to which models become more aligned, basically better at lining up with those high-level, I'm not a racist descriptions that they would give at the beginning of training, and the extent to which their explanations are actually predictive of their behavior at the object level. And what we see is that basically for any value of the trade-off between this explanation gradient and this behavior gradient, we can Pareto dominate certainly both the base model and other standard training procedures that are designed to sort of automatically align models just by looking at their explanations or their behaviors in isolation. And I'm going to skip over this in the interest of time. And so coming back to this example that we started with here, right, here is our behavior before, where there's a mismatch between these two answers. If we train models so that only their behaviors change, it starts refusing to respond to this request at the bottom. And if we change models so that we're only taking a loss on this explanation term, then the explanation actually changes to reflect a much looser policy about when it responds to user requests, and to say that, in fact, it only refuses to generate requests specifically involving sort of responses to, or incentives to generate violence. Good. So to sort of start to wrap up here and set up some questions, I think the high-level point, or the high-level interesting thing, and you can ignore this graph in the top left because I cut it out in the interest of time, is that we see in all of these cases that models are not simply memorizing the explanations in their training set, but generalizing either to sort of new questions of the same kind on new prompts, and even entire new sort of categories of behavior that we might want to get them to describe. And so how should we sort of conceptually understand what is going on in an LM when we've subjected it to a training procedure like this? There's quite a lot of other work going on right now on sort of introspection, self-awareness, self-reports broadly in LMs, and I think quite a lot of sort of confusion and disagreement in the community about what this even ought to be called. This is something that I would love to get from this group, and especially the people who think about human cognition more in this group. To what extent do we want to think of these behaviors as models having some kind of privileged access to their own internals, to performing something that looks like introspection, metacognition, or whatever else? And I think there are a couple of different mental models that we can have of what might be going on when you exhibit one of these behaviors, all of which I think are broadly consistent with the data that we have today. This is related also to some of the stuff that Lenore was talking about, but right, we can imagine a version of this where the language model in its sort of raw state generates behavior and learns as a result of explanation training to also sort of store a second copy of itself internally that it uses as a model. We can imagine a version of them of these sort of results where there's just one sort of data generating mechanisms inside the model that can either be consulted to generate behavior or to generate these kinds of explanations. And of course, we can imagine a picture of this where these things are all just kind of bags of heuristics, and there's not really any coherent sense in which any of this is deriving from any structured model of the LM at all. I think what I've showed so far and some other results that we have on how this explanation behavior survives under changes to the model, that this is the right picture to have, but I think there's still quite a lot of uncertainty about how to think about all of this. There's a fun analogy to quines and computer programs that I will skip in the interest of time and wrap up there. As always, all credit goes to the people whose work I talked about today, Itamar, Belinda, and Carl, and all of our other collaborators. Thank you.
Why don't we take a question while
Yeah.
This example that you gave, that it answers inconsistently for the same question, posed different, I guess you could solve it by just more training.
Well,
Why is this better than just give more examples and
I mean, what are you going to train it on, I guess is the question, right? For
give different versions of the same question and demand the same answer?
Well, but I think, either you are eventually going to have to train on, sort of, basically to the extent that we don't think the answers that models are going to give are entirely predictable from any kind of training data that we, might be able to generate, this is in general going to be very hard. And I think, especially thinking about this confidence example right now, there is some sort of empirical fact of the matter about the probability that the model is going to answer this particular question correctly or not. I guess you can derive that fact from the training set, but really only by training the whole model on it. And we, as humans who are looking at this model, don't really have any way of sort of inspecting it and figuring out what is the probability that this particular question is going to be answered correctly. And so I think what you are describing amounts to saying, well, why don't we just add more training data until the, sort of empirical probability of success is 100% on all questions, and I think we basically have no reason to believe that there will ever be enough data to do that.
It's not that it's 100%, but you don't like that it's higher below than above, right?
Well, just that, if you do the sort of standard calibration measure and asking, for all of the questions where the model's claimed probability is, or claimed confidence is 60%, about 60%, does it get about 60% of those accurately? And the answer is absolutely not, unless you do some kind of focus
I would just interpret both of this as don't know, right? If you say yes with 64% confidence, means that you don't really know.
Maybe we should talk about this offline.
We can continue answering,
Yeah.
but without your screen.
You can continue to take questions.
Oh, okay. Yeah.
So do you think that when the model tries to explain, itself better than, is that like a social, emotional intelligence?
Oh, that's probably a question that's above my pay grade to answer. I mean, I think there is an interesting, coming back to the sort of models that we had before, if you have, for example, the rightmost picture where, there's the behavior generating mechanism and then there's, the model has a smaller copy of itself internally that it's consulting when figuring out how to answer these questions, where does that simulation mechanism come from? And is it something that is being learned sort of totally de novo during this explanation training procedure, or is it something that, in the course of pre-training, you have to learn to simulate everybody who ever wrote a web page on the internet? You learn some general purpose agent simulation machinery, and then you hook into that when you're trying to learn how to simulate yourself. I think that is also totally plausible as a sort of explanatory mechanism for what's going on here. How that relates to sort of socio-emotional intelligence more broadly, I'm not sure. Okay.
Excuse me? What?
Oh.
Like, what?
Lunch.
Okay, lunch.
Okay, so thank you. Thank you, Jacob. And now we're going to go back to the cerebellum, I think.